Good morning. Welcome to the fourth part of module 2. Today we will discuss about overfitting. So, we mentioned overfitting when we talked about a decision tree in passing. So, first we will define what is overfitting. So, if you learn a decision tree and you continue splitting nodes, the tree will become larger and larger. When the tree becomes larger, if you use the tree for classifying the training examples, the error on the training examples will reduce. But it may happen that after some time, as you grow the tree, the true error will increase. So, this is called overfitting. Let us formally define overfitting. We say that a hypothesis H is said to overfit the training data if there is another hypothesis H prime such that H prime has more error than H on training data, but H prime has less error than H on test data. For example, in the context of decision trees, if it happens that we have a smaller decision tree and it has a higher error on training data and lower error on test data compared to a larger decision tree which has smaller error on training data, but higher error on test data, we say overfitting has occurred. So, let us look at this slide, that suppose as we are growing a decision tree and as we are splitting the nodes, we are splitting the nodes when there is positive information gain, that is there is a resultant reduction in entropy. Typically what we expect, as we keep growing the tree, the accuracy of the tree will go on increasing on the training set, that is the error will go on decreasing on the training set. However, if you test the tree at different points in the algorithm on a held out test set, disjoint test set, what we typically observe is that as you grow the tree, initially accuracy on the test set increases. After some time, the accuracy on the test set starts to fall. Now, why can this happen? You see that we want to have good generalization performance, but the training data may contain noise, and as we make the decision tree more and more complex, it may try to fit noise, and therefore, the resulting decision tree will not work well on the true population. A second reason could be you have too few training examples and you are trying to accommodate the errors in the training example and you do badly on the test set, right. This is why overfitting can occur in decision trees. Now, to illustrate overfitting, there was an experiment which was run where some positive and negative examples were taken and they were generated such that all points with radius from 0 to 0.5 were blue class, and those having radius from the origin between 0.5 and 1 were red circles, and beyond 1 also it was blue triangle. So, this sort of examples were used to construct a decision tree. And in this decision tree, what we observed is that the error on the training set, the last curve we were plotting accuracy. So, accuracy was going on increasing as we increase the size of the tree. Here we are plotting error. So, error on the training set will go on reducing as we construct the decision tree. But if we check the error on the test set, initially the error on the test set decreases, after that it increases. And where it starts to increase, in this region we say overfitting has occurred. In this region where the tree is not big enough, we say there is underfitting. In this region on the left there is underfitting, in the middle there is a good fit, and on the right of this dashed line we say overfitting has occurred. So, underfitting occurs when the model is too simple, and overfitting occurs when the model is too complex. And here is another slide to illustrate overfitting. Now, when you have overfitting, what will happen is that, suppose we take another example. Suppose these are plus is positive point and these red circles are negative point, and suppose there is a noise point here, right. If we have this noise point which is a spurious point, and if we really want to have the decision tree to have low error, then the decision tree will try to include the noise point, and if it includes the noise point, it will induce error in the true set. And overfitting can also be due to not enough examples. For example, if you look at this slide, the bottom portion we do not have too few examples, and because we do not have too few examples, this green line is the ideal. These crosses, blue crosses are the one class, and the red solid circles is the other class, and the red hollow circles are your test points. Because you do not have too enough examples, these points may be misclassified. If in a region in the feature space you do not have sufficient examples, then you cannot form a proper hypothesis about that region, and this may lead to overfitting. So, if you are working with decision trees, overfitting results in a more complex decision tree that is necessary, and training error is not a good predictor for test error. So, what you have to do, training error is not a good predictor for true error, and therefore, you should use a separate unseen sample called the test sample in order to get a better estimate of the true error. Now, so we have to now see, now that we know that overfitting has occurred, we have to look at what can be done to avoid overfitting. Now, let us look in the context of decision trees. There are two types of methods that are used to prevent overfitting. So, first of all, you could prune the decision tree while growing. You can stop early. So, you have pre-pruning type of methods and you have post-pruning type of methods. So, pre-pruning is a method of pruning decision trees to deal with overfitting, and what pre-pruning involves is stop early. And when do you stop? You stop when the data split is not statistically significant. What we saw with the entropy measure is that we split a node on an attribute and we compute the resulting entropy. So, there is S is the examples here, S1 and S2 is a set of examples here, and we find the gain of S with A, and we find the attribute with the highest gain. The attribute with the highest gain should have a positive gain. If there is a negative gain, there is no reason to use the attribute. But even if there is a positive gain, if the gain is not significant, if the gain is not statistically significant, we will stop at the node. So, you stop early, that is, stop growing, stop splitting when gain is not statistically significant. That is, you do not grow the full tree. A second type of method of pruning decision trees is based on post-pruning. In post-pruning, what you do is you continue growing the tree till the tree is quite large, but after that, after growing a big tree, you prune different sub-trees of the tree. So, grow the full tree and remove the nodes. Now, how to remove the nodes? There are several heuristics which have been used to decide which subtrees to remove. So, you may decide to say that, suppose you have grown a decision trees which is quite big, so suppose this is some decision tree that you have grown and you want to decide whether you want to prune the subtree, that is, you want to make this as a leaf node. Now, what you can do is that you can use cross validation. So, what you can do is you can use a validation set and you check the error of the original tree, and suppose this is the subtree ST1. So, you find out the error, of T and error of T minus ST1, right. So, you find out the error after removing the subtree. If this error is smaller, then this is a candidate for removal. Now, when you have a decision tree, any internal node is a candidate for removal. You can remove this node, this node, this node, this node, this node, this node. These are different, or even this node. So, these are the different candidate subtrees for removal, and among them you want to find out those subtrees whose removal improves the test error, right. Among those, if there are no tree whose removal improves the test error, you do not prune further. Among those trees which are eligible for, among those subtrees which are eligible for removal, you choose that subtree whose removal lowers the error the most. So, that is by using cross validation. Apart from cross validation, there is another method based on a principle called MDL, or minimum description length. We will not talk about this principle in detail. The basic idea is, you want to look at, you think of having a function or having a decision tree or having a classifier as reducing the size of information. Suppose you have a training set and you have a function which classifies the training set perfectly. Using the training set, you can recreate, using this function, you can recreate the training set. Given x, you can find y, right. This is the role of this function. Now, if this function was perfect, you could just skip that function, you could remove the labels on the training set and you could recreate that. But if your function is not a perfect classifier on these examples, what you should do is keep this function and keep the labels of the misclassified examples. So, you could think of that given a function, the total information that you have to keep is the function plus the misclassified examples. Now, you could compare two different trees, one tree which is smaller and classifies less examples, and a second tree which is larger and classifies more examples. You could compare them based on the description length. What is the total length, total number of bits required to keep the function and the misclassified examples, and you want to choose the tree for which this is smallest. So, that is another principle, but we will not talk about it. So, let us look at this slide on pre-pruning. As we said, pre-pruning means early stopping. You evaluate the splits before installing them. So, do not install splits that do not look worthwhile when no worthwhile splits are there to install done. So, typical stopping conditions for a node are, in a normal decision tree without pruning, you stop if all instances belong to same class, you stop if all instances belong to have the same value. And if you want to use pre-pruning, you introduce some more restrictive conditions. For example, if you stop if number of instances at that node is too small, you stop if the class distributions are independent of the available feature using some statistic, we will not talk about it in detail. Thirdly, you stop expanding the node if the improvement in the information measured is not statistically significant. For post-pruning, one of the algorithms for post-pruning is called reduced error pruning, and we will describe that algorithm. In reduced error pruning, if you look at the slide, is a post-pruning cross-validation approach. So, given the training set available to us, we will split the training set into a training and validation set. We will split the training set in the training and validation set, or we call this a grow set. This part of the training set is used to grow the tree, and this part is used to validate the tree. Now, using the grow data, we will build a complete tree, which ideally has 0 error on the training data if possible, otherwise also grow the tree as much as possible. After that, you start pruning the tree, and as we said, you look at different candidate subtrees for pruning. And how long will you continue pruning? Until you reach a situation where removing any subtree will give you increased error on the validation set. So, until accuracy on validation set decreases, you will do this. For each non-leaf node in the tree, as we explained, any non-leaf node or interior node is candidate for pruning. For any non-leaf node in the tree, you temporarily prune the tree below that node and replace that node by the majority vote. Test the accuracy of the hypothesis on the validation set. And so, that is so you find out if the resulting error is smaller than the original tree. And now you do it for every attribute, you prune that subtree for which this error is lowest. So, you permanently prune the node with the greatest increase in accuracy on the validation set, and you continue doing this until accuracy on the validation set does not increase. Now, so this is a post pruning method. There are a few cons of this method. Because you are dividing the data into grow set and validate set, you have less number of data on which to grow the tree. Now, if you look at this slide, it shows the effect of post pruning on a particular training set. This solid line in the top this is the training error on the training data as you grow the tree. So, tree is grown 2, 0, 1, 2, 10, 100, up to 100 node tree is grown, and as you see the training accuracy is going on increasing. Whereas, the test data on the validation set, the accuracy is reducing. After initially it is increasing, after some time it is reducing, that is overfitting has occurred. Now, after we have grown the full tree, we are using the reduced error pruning algorithm to post prune, and as we are post pruning, the number of nodes in the tree is decreasing, and we see that accuracy is increasing up to this point. When we have about 18 nodes, the accuracy has increased. After that, further pruning does not give you better accuracy, so we stop here. So, this is the effect of post pruning on the accuracy of a decision tree. Now, we have discussed earlier that learning involves generalization or induction, and it is an ill posed problem because you do not have sufficient data. So, we need some bias to restrict the hypothesis space or put some preferences, so that you want to prevent overfitting. And there are 3 trade-offs which are involved. These trade-offs include these 3 factors: the complexity of the hypothesis. A more complex hypothesis is more flexible, it can accommodate more powerful functions, but more complex hypotheses are may lead to overfitting. The second is training size. If training size is too small, then using that training set you cannot come up with a good function, there may be overfitting. The third is generalization error, that is the true error, the error on the population or unseen instances. So, we want to look at the trade-offs involving these 3 factors: the complexity of the hypothesis, the size of the training set, and the generalization error. We find out that as n increases, as training size increases, the error decreases. As complexity of hypothesis increases, first the error decreases, then the error increases. As we saw in the decision tree, as we are growing the decision tree, initially error is decreasing, then it is increasing. And as complexity of hypothesis increases, the training error decreases for some time, and after some time it may become 0, it becomes static. But the test error or the true error first decreases and then increases. And this is when error starts increasing, this is the region where we say overfitting is occurred. This is where overfitting has occurred. So, overfitting is happening when a model captures the idiosyncrasies of the data rather than the generalities in the data. If you have too many parameters, if you have too many nodes in the decision tree, if you have too many parameters, overfitting can occur. For example, we discussed about regression in an earlier class. If you have linear regression, you have few parameters, beta 0 and beta 1, beta 2. But if you have second degree polynomial, fifth degree polynomial, 10th degree polynomial, you have many more parameters, and overfitting is more likely to happen, because an nth order polynomial can intersect any n plus 1 data points. If you have too few data points, you should use a function which has fewer parameters, because otherwise overfitting can occur. We have seen how overfitting can be dealt with in decision tree. In regression also overfitting can occur, and in regression or linear regression overfitting can occur. And if you want to deal with overfitting, there are some standard ways of dealing with overfitting. First of all, for any learning algorithm, if you can get more data, that is one way of dealing with overfitting. The second is the idea of cross validation, using a validation set to decide what is happening. So, this is a very general approach to deal with overfitting, and then we will later look at a Bayesian approach to overfitting. But one approach we will just want to spend 2 minutes on is regularization. Regularization is a method of dealing with overfitting in algorithms like linear regression. Now, in a linear regression model, we typically overfitting is characterized by large weights of the coefficients. The coefficients beta 0, beta 1, beta 2, etc., that we use in linear regression, if overfitting occurs, normally these values become too large. So, to deal with overfitting, so if you look at this slide here, this shows the values of the different coefficients at different instances. And as you see, this is for a 0th degree polynomial, this is 1 degree polynomial, 3 degree polynomial, 9th degree polynomial. When we fit the data with a 9th degree polynomial, we are seeing that the weights are coefficients are very large, and this is an indicator of overfitting. So, in order to prevent overfitting, one of the methods that we can do with polynomial regression or even in linear regression is use regularization. And one way of regularization is to penalize large weights. So, earlier we have seen that the error function which we try to optimize is the sum of squared errors, that is the value of y minus y hat whole square sum over all the examples. So, Tn is the target value and this is the value of the predicted value. Now, if you want to deal with overfitting, in addition to this, in the error function you can add another term based on the coefficient, the size of the coefficient, right. So, there are different types of regularization, L1 regularization, L2 regularization, etc. For linear regression, there are two very popular types of regularization method, L2 regularization or ridge regression. It adds a factor lambda by 2 w square, where w square is the L2 norm of the coefficients. And in L1 regularization or lasso, we use the L1 norm. So, this is added to the penalty function, and this is the function that you try to optimize. So, you prefer the weights so that the weights are small and the error is small. If you do that, it can help in preventing overfitting in linear regression. With this, we come to an end to this class. Thank you.